Okay. So, last class we ended up with support forces, forces coming from different type of supports on structures when we had 2-dimensional loading. I talked a bit about 3-dimensional loading, but let's start. Let's take a case where forces are acting in all the 3 directions on the members, and there could be moments etc., which are there on in all the 3 directions. One kind of support which we have is there is a frictionless surface on which we have a body which is moving or which is there, it is held static, and a similar type of force comes in case if there is a body on a rough surface, but there is a ball on which the body is kept, and we assume that there is no friction between the ball and the surface. Even if the surface is rough, the ball provides a smooth surface. So, in this case what happens is, there will be a friction force which will act in the plane of contact. Now, in this case the plane of contact, if I say this is the xy plane, the xy is the plane of contact, and because the frictional forces are 0, there will be no forces provided in x and y direction. And again the same principle holds. You try to move the body along x, will there be a resistance? You try to move the body along y, will there be a resistance? There will be no resistance if there is no friction. But you try to move the body along z, and obviously here the loading is such that it will go down. If it is up, it will move up, there will be no contact forces. But if you try to move the body down vertically along the z axis, you will find that it will not be able to move. That means there will be a force. Whereas if you try to rotate the body, it will rotate about all the 3 axes, so there will be no torque, and therefore in cases like this, the unknown reaction will be a single force. What I mean by single? Its direction is known. If the direction is known, that means there is just one unknown, one scalar unknown. A similar is the case of the cable, which we have seen in 2-dimensional also, and in 3-dimensional cases. If there is a cable which is pulling a body, then we have a single force acting along the direction of the cable. So, again the number of unknowns here is only 1, because the direction of this force is known to us from the geometry of the problem. Let us move ahead. We have this case where we have a roller on a rough surface, or we have a wheel or a rail. Now, this roller is different from a ball which was able to rotate freely or move freely along its direction. Now, the roller has a circular movement, so it can move freely along the x direction, but not along what has been termed here as z. The vertical is y. So, therefore, when you draw the free body diagram for this body, what you will get from the support will be a force along y and a force along z. Okay. So, that is how we have the, and similar is the case for wheel on a rail. If the wheel is on a rail, then free motion is allowed only along the direction of the rail, which is taken as the x direction. Along the other 2 direction, motion is prevented. So, therefore, we have forces in the y and z directions. Now, torque, we are assuming that this is a very small contact, so it will be able to locally turn. It was a good question that what about the torque? But if this rail was a big enough thing, as we will show later, then torque will also come. And we will, in fact, this sort of a thing we will see later also in the course, that we will normally assume that the body will bend at this point, so there will be no torque which will come. Now, no, the torque could come, because if you try to now rotate this so about, let us say, an axis which is marked as z, then it will be prevented to be rotated. So, the torque should come, but we assume that there is a point contact, and locally there will be a small deformation, so that it will just deform and there will be no torque. Now, we talk of the third case which I talked about in the last class also. I talked about this joint which I called as a ball and socket joint, where a free rotation is allowed on all the 3 axes at the joint, or we could have a rough surface on which the body is kept. So, in this case we will have unknown forces from the support in all the 3 directions, and because rotation is allowed, there will be no moments. So, this is what we have when we have unknown forces in the 3-dimensional scenario. Some more of these. Now, the top figure shows what is termed as a universal joint. Now, in a universal joint, you see there is a rod here. Let us call these as x, y, and z. Vertical axis is the y, the axis coming out of the board as z, and x as the horizontal axis. Then we have both the rods are aligned along the x axis. But if you look at the pin which is connecting the rods, then in one of the cases the pin is along the z, in the other case it is along y. Such a joint, so that means it is a joint like this with two axes, one axis vertical, one axis horizontal, and kept like this. Okay? And in this case, when you see, the joint does not allow any movement along x, y, or z, because these two things will prevent the movement. So there is no linear movement, therefore we will have fx, fy, and fz. Now when we try to rotate about the axis of each of these joints, about this pin is about the z axis, the body will rotate. Similarly, about the vertical axis, because we have a pin, the body will rotate. But if there is a moment about the x axis, then this joint will prevent a rotation about x axis. And therefore, when we draw the free body diagram at the joint, for one of the bodies we will get fx, fy, fz and mx. For the other body, we will get the opposite thing, because action and reactions are opposite. So this is how a universal joint works like. Then in the last class, we had taken the example of a cantilever, a fixed support inside a wall. In that case, not only linear motion, but any rotary motion was also prevented. Now if we look at a generalized three-dimensional case of that, then there is a support and the body is, let us say, hammered inside the ground. It is something like a pole or something which has been fixed inside, and there is no joint which is allowing any motion. So now in this case, when I try to move the body in the x, y, or z axis, no linear motion is allowed, so I will get fx, fy, fz. Similarly, if I try to rotate the body about x, y, or z axis, I do not get any rotary motion. The joint prevents that. So if the joint is preventing a motion, a rotary motion, it will provide a moment in that direction. So we will have mx, my, mz, fx, fy, fz. These will be the forces and moments being provided by the support on the body. Okay. Now this is what we have is a hinge and a bearing supporting a radial load, and this is what I said was a general example of what was the rail was there, but now this is a bearing which is there, but the dimension is not very small. So in this case, we have a rod which is coming like this. Now when we look at it, now it says it's a radial load. That means we are assuming that on this bearing it can move axially. This rod can move along what is termed as the x direction. If it can move along the x direction, there will be no forces along x direction. So you will get fy and fz. And also if we look at because it's a circular bearing, it allows a free motion about the axis like this. So that means there will be no moment provided along x axis by this bearing, whereas it prevents a rotation of this along y and z. So therefore we have two force components and two couples. Okay. In some of the problems, for example in this problem, on this side of the bearing, maybe you also provide a restrainer which does not allow motion along x axis. That means you put a small cap at the back of this bearing. Why would you put this cap? So that you would not like the rod to move out. In that case, on the bearing where you put a restrainer, an x force will also come. Okay. So these are the different type of supports, and once you solve some problems, you will start getting a hang of these, and these are needed in the free body diagram. You need to put these to be able to solve your problems. Now the last of this, the pin and the bracket, the pin joint which we saw last time, I had in fact discussed this. When we have three-dimensional loading, then once again in a pin joint like this, we will get all the three forces will come, and it allows only a motion about the horizontal axis, the x axis, a rotary motion. So therefore we will have my and mz, they will also come. And this would also be the case if there is a radial as well as an axial load on the bearing, which I already talked about. So there you will get three forces and two moments. Okay. Now, there is one case which is not discussed, and let me, at least not in the textbook. So, let me draw this, and this is if I have interior section of a body. That means, I have some body like this, I have this sort of this elliptical type of body, whatever, it is a 3-dimensional body on which I have forces F1, F2, F3 and a couple C1 acting. Now, if I make a cut section on the body, which I show as the dotted line, and I want to draw the free body diagram of the two cut sections of the body, I want to draw either of the left hand side or of the right hand side, then how do I draw that? So, when I draw the free body diagram of this, what I will get here is this is the left side, this is the right side. So, I want to draw the free body diagrams of the two sides. Now, what happens on the left side, I will show all the external forces, so F1 and F2. Now, what happens is at the cut, I have to show what is coming out from the other half of the body on this, because now I do not care, I can't show F3 and C1 on this free body diagram. Why? Because F3 and C1 are not acting on the left half. When I talk of a free body diagram, I talk of only the body which I am interested in, and right now my body is only the left half, not the complete body. So, now what will happen? How do I effectively model what is happening on the cut part? Anything else? He said forces from the B part acting on A. In general, when I do a cut like this, I will show two things. You are partially right that I will show an unknown force R, which I show as a vector, means I do not know its direction. In addition to this, there will be also an unknown couple C, because this is what the general action reaction effect of the body on part of any, whenever we cut a section, the cut section will exert an unknown force and an unknown couple. Okay? Now, yes. No, it will depend on how it is. I am talking of a general 3-dimensional case. It would be in some cases the couple may also be 0, depending on the type of loading. We will see some cases, for example, when we talk of a thin bar, when we cut a section, in certain cases you will only find not only a force, but force acting only along the direction of the bar. So, that could happen, but in general we will have a force and a couple, and this R will be Rxi plus Ryj plus Rzk, C will be Cxi plus Cyj plus Czk, all 6 unknowns. But what will happen when I draw the free body diagram of this part? Is there a relation with the first part? The reactions will be equal and opposite, so that when I club the two things together, I should get a 0. So, therefore, when I draw the free body diagram, so this R, let me first write here, R is a general force Rxi plus Ryj plus Rzk, and C is equal to Cxi plus Cyj plus Czk. But now, when I draw the free body diagram, let me draw it again, of the right part, first I will show C1, I will show F3, and now here we will have minus R and minus C, and this minus R is equal to minus Rxi minus Ryj minus rzk, and minus c is equal to minus cxi minus cyj minus czk, so that when the two are clubbed you get a 0. So, this is what in general, this is for a general loading. Special cases we may get some of these may be 0, but this is what a cut section will entail. Now, why do we need forces on cut sections? Normally we talk of the whole body. Why should I talk of forces in a cut section? Exactly. There is a limit to the mechanical strength. Now, your section may be such that it may be very thin at a section. Now, on that cut section you find what the forces and moments are, and that section should be able to bear those forces and moments. Overall the balance may be right, but individually if at a particular part, if the forces and moments are not correct, then maybe it may fail there, and that is why, or in terms of a better design, what you would like to do is, what is the minimum area which should be for a given loading, what should be the minimum area which I should be developing this bar for, so that it can take this load. Because if you say extra area, that means you are putting in more material, which means more cost. So, you want to prevent that cost. So, that is why these internal forces will be important, and we will see them in a couple of lectures when we talk of shear force and bending moment. We will talk of the internal forces. Okay. So, now having done this, we are now in a state where we can talk of so now we will talk of the equations of equilibrium. We have done all these supports. In fact, probably in the problem solving sessions you may have already done the equations of equilibrium, and our equations of equilibrium now are very straightforward. Equations of equilibrium are and these come from Newton's laws. Right now we are talking of statics, so I will just state the equations of equilibrium. I will say they are necessary condition but not sufficient. I think some books say they are necessary and sufficient. So, we will leave that discussion till we reach dynamics, and where I will qualify my statements, but the equations of equilibrium are, the first vector equation is sum of all the forces is equal to 0, and sum of forces, sum of moments about a point O, where O is any fixed point in space. Okay. So, now in case of a planar loading, the equations become sum of forces in the x direction is equal to 0, sum of forces in the y direction is equal to 0, and automatically when you take sum of moments about any point A is equal to 0, this will only be the z component, because moments in a planar loading will only be about the z axis. So, examples of this could be suppose I have a beam like this, on which two forces and moments are acting. You are asked to find reaction at the support. You have done similar problems. So, how you will work this out? You will draw the free body diagram of the beam. So, find reaction at supports. So, you draw, let me call this A, let me call this B. So, now at point A, I will have Ax and Ay. I have shown Ax in the minus x direction, it does not matter. unknown forces and reactions can be shown along any direction. If your assumed direction is wrong, you will get a minus sign. So, unknown forces I show as Ax and Ay. Then I come to this point, I will show F1, then I will show M1, F2. Now, at B, what I see is there is a joint with a roller support. That means I will have forces only in the y direction, because if a force is applied at point B by the support in the x direction, the roller will move. So, therefore, there will be no force in the x direction. So, at B I will get only By. And then now, if I write sigma Fx is equal to 0, I will get F1 cos minus, or let us assume x is positive direction. So, F1 cos alpha minus F2 cos beta plus Ax, or plus Ax is equal to 0. That will give us the x equation, the y equation, minus F1 cos beta minus F2 cos gamma, whatever those angles are, plus Ay plus By is equal to 0. That will give us the second equation, and we take moments about A or moments about B is equal to 0, and that will give us. So, in fact, here if I directly take moments about A is equal to 0, I will get By, assuming forces F1, F2 and M1 are known. So, now if the problem says find By only, then all you do is take moments about A, one equation gives you the answer. Okay. So, therefore, you will use these three equations in different combinations. Sometimes you can take moments about A is equal to 0, get By, take moments about B is equal to 0, that will give you Ay, and then you do sigma Fx is equal to 0, that will give you Ax. So, you use combination of these three equations, but you will not get more equations, you will get only three independent equations. Okay. Yes. But at A, no, because it is just a support, it is a pin support, it is just kept there. So, it will, there will be no moment at A. Moment will come if you have a support like this. If you have a fixed support at A, then there will be a moment at A. But in the case of a pin or a roller or anything like this, there will be no moment at A. Okay. Okay. Next, so this is for a two-dimensional case. For a 3D case, I will take an example after this, but before that, in a three-dimensional case, we get 6 scalar equations. Sigma Fx is equal to 0, sigma Fy is equal to 0, and the x, y and z components of moments about any one point are equal to 0. And these moment equations in three-dimensional case, you can also replace by taking some particular axis and taking moments about that axis is equal to 0. We know how to find moments about axis, we have already done that in the first chapter. So, therefore, we can just move from there. These can be replaced by taking different axes, and you may be able to then get problems in an easy way. Now, there is one more case which comes, and let me first do that before I come to the, and this is what I call two force members. Suppose you encounter a component on which, so we have, let us say, there are these three links which are connected. AB I have shown as a circular link, AD is the second link, BC is the third link, they are all connected by pin joints. There is a two-dimensional case I am talking of right now, and let us say on BC a force is acting, on AD a moment is acting. So, this is the loading and all the three members, that means AB, BC and AD are light. That means, what do I mean by light? It is not light as opposed to not dark, but it is light as opposed to not heavy. So, that means their weights can be neglected. Okay. So, now when I look at this loading, when I draw the free body diagram of BC, what will I get? In free body diagram, I have not shown what is happening at C. C probably, let us assume that in this case C is connected to the wall and D is also connected to the wall. So, now when you draw the free body diagram of BC, what will happen? You will have, what will happen at point B? You have Bx and By. At C, again Cx and Cy, and we have the force which is there, it is acting at some point in between there. So, at how many points are forces acting on the member BC? At 3 points, at B, at C and at the middle point. Similarly, let me look at the member AD. In the member AD, what will happen? I have forces acting at A and at D, and I have a moment acting at M. So, again if I analyze, I have forces acting at A, force acting at D and a moment acting at M when I draw the free body diagram of AD. However, when I draw the free body diagram of AB, what do I find? That there are force acting at A, AX and AY, which may be opposite of what you have shown here, and similarly force acting at B, which is opposite of what you have shown acting on BD. But that means, in the free body diagram of AB, I get only 2 forces which are acting at 2 different points. So, forces are acting at 2 different points. You may say there are more forces, AX and AY are 2 forces, but then it is acting only at A. So, I can combine it in a vector and call it as a single force. So, a 2 force member is a member on which, or is a part of a component or something where forces are acting only at 2 different points. Or even when you talk of a equivalence, suppose you may talk of a case where there is weight acting, but then if it is acting, equivalent of it is acting at the center of gravity and there is only one connection. So, you can call that also as a 2 force member. So, that means in a 2 force member, only at 2 points forces can act. That is the definition of 2 force member. So, force, or on a 2 force member, only forces act at 2 different points on the body. Only forces means that there are no couples. Now, in this case, when I draw the free body diagram of AB, what I will have will be an unknown reaction A, unknown reaction, let me call it RA and RB. Okay. What is the such a big deal about this? If this body is in equilibrium, let me write its equations. What are the equations? The first equation I write, I get RA plus RB is equal to 0. What does this tell me? That RA is equal to minus RB. That means in a 2 force member, the 2 forces which are acting along the 2 points have to be equal and opposite if the member is in equilibrium. Okay? Is that fine? That is the first condition. The second condition which we will get here is, if I take moments about A is equal to 0, what does this mean? That RB must through A. Similarly, when I take moments about B is equal to 0, I will get RA must pass through B. So that means, what is the line of action of RA and RB? It has to be the same, which has to be the line AB. So this means that the line of action or the direction, that is what this means, of RA and RB must be the vector AB. Okay. So that means, now when I talk of the unknown force, I get only one single unknown, which is a single RA or RB with its line of action known. Now, where does this simplify things? It simplifies things. For example, if you have to find, you have to draw the free body diagram of BC. Now, if you have to draw the free body, you have to solve this problem. Suppose this loading is given on this, you have to find forces at reactions at support C and at support D. If this was your problem, that you have to find the forces at C and D. Now, when you draw the free body diagram for BC, you will show unknown forces at C, you will show a force at whatever force is acting. Now, what will happen to the force at B? It will be just a single unknown, because the force at B has to be along the line joining AB. So, therefore, when I draw the free body diagram of BC, I will show Cx, Cy, I will show this force, and this unknown force, which is RB with direction known. So, this is how the two force member concept will help me in finding, in drawing or in solving the link to which the two force member is connected. It will not directly help me in finding forces there, but when I draw the link to which this two force member is connected, I will get a case like this. Okay. So, you can use two force members to simplify problems to help your life, or sometimes even on the same member, if you know, then you know it has to act along this given line. And once you do that, you do not need to write equations of equilibrium for the two force member, because they have already been included when you determine, say, its line of action has to be like this. So, that has already been known to you. So, you work these out, and that is how two force member can help you to simplify solving the problems. Now, there is one more concept which I would like to do before I take another example on 3D. So, and that is, I will talk of static indeterminacy. And we take an example of what we term as a, let us take, to illustrate this, we will take planar loading. And this is the case which we have already seen just now. If we have forces F1 and F2. Now, here when I draw the free body diagram, I am doing it fast. I will get Ay, I will get By, Bx, these are unknowns, F2, F1 they are known. So, now when I count my equations, I have three unknowns ay, bx, by, and how many equations do I have? From statics I will get three equations, and these will be sigma fx is equal to 0, sigma fy is equal to 0, and sum of moments is equal to 0. And I have enough equations and enough unknowns. I will be able to solve for the three unknowns by these three equations. Such a case or such a scenario, we call it as a statically determinate loading. That means, in this loading I can find the unknown reactions from equations of statics. I have enough equations and enough unknowns. Okay. Now, what would make this loading statically indeterminate? So, obviously, statically indeterminate would be a case where the number of equations is not sufficient. And if I make the left hand support another pin support, if it is not a roller support, then what will happen? So, we contrast it with the case if left hand support also pin also at fixed pin, no roller. Now, I will get AX, AY, BY, BX, F1, F2. And this is a case, now I have four unknowns and three equations. So, this is what is termed as statically indeterminate system. And here we cannot solve the unknowns just by the equations of statics. We have to go into local deformation theory and mechanics of materials to be able to determine the fourth unknown. So, for example, in this case what you will realize is you can't find AX and BX. All you can say is that their sum will be equal to this much, but you will not be able to find out what is the exact value of AX or exact value of BX using static cases, and it's using just our equations of statics. So, that is why we term it as statically indeterminate. Okay. Now, let us look at a case. So, that means number of unknowns is more than the number of equations in statically indeterminate systems. Let me take another case, and let us take a case like this. Suppose we have I deliberately make these links of curved shapes, they need not be. Suppose we have links AB and BC connected by a pin at B. Now, is this a statically determinate case or statically indeterminate case? If I draw the free body diagram of the total system, I will get Ax, Ay, Cx, Cy. Okay. And then I have forces F2 and F1 which are known. Forces at B will not come into picture because I am drawing the full free body diagram. Forces at B are internal. So, therefore, I will get just 4 unknowns, 3 equations. So, looks like a statically indeterminate system. Okay. So, if I draw, so full, let me write this down, full system if I look, there are 4 unknowns, Ax, Ay, Cx, Cy, 4 unknowns, 3 equations. However, yes, how do we know the direction acting on A? It is, why? It is a 3-force member. If you just look at the link at A, then on that link a force is coming from B also. So, then it is not no longer a 2-force member. See, if you are drawing the free body diagram only of AB, then forces at B will also come into picture. The link BC is exerting some force on the link AB, so that force will come. If you look at that force, then what will happen? You have a force at B, a force at A and F2. So, force at A will not be towards AB. You don't, okay, let me solve it. I think that is the key to the solution. That what is happening here is that in this actually we have 2 subsystems together. Let us look at the free body diagram of AB alone. Free body diagram of AB, and this is what you wanted me to, this is A, this is B. So, then on the free body diagram of AB I will get F2, I will get Ax, Ay. Now, I will also get here Bx and By. Okay. So, that assertion now I think you are clear that it will not be towards him. So, now let me count the number of unknowns 1, 2, 3, 4. So, this is by itself it is not statically determinate. There are 4 unknowns and we have only 3 equations. Now, let me draw the free body diagram of BC. Let us draw it here. I have Cx, I have Cy, I have a force F1. Now, what happens at point B? I will have Bx scalar in the opposite direction and By scalar again pointing upwards, which are equal and opposite. So, I just call them the same thing, Bx and By. Okay. So, now when I add the total number of unknowns in the 2, now I have 3 equations here, I have 3 equations here. So, totally I have 6 equations. And how many unknowns do I have? 6 unknowns. So, actually the system therefore is statically determinate. Now, what is the magic which made the system statically determinate? We can use this trick, we can break the system any point at any time and we will be able to get it. Will we be able to make any statically indeterminate system into determinate by this trick? The answer is no. Why? Because here the joint at B is a very special joint. It is a pin joint. That means it is allowing you one extra equation because it is not providing an unknown moment. Suppose if I cut the body somewhere here, then I will also get a moment along with a force. So, in that case I will not have the number of unknowns will not reduce, but it is the joint at B which is a pin joint which does not allow a moment. So, that is why you get an extra equation without adding, or equations are the same, you do not add an extra unknown, and that is why it becomes a determinate system. So, internally you can say this is a statically determinate system, whereas externally if you look at the total system, it may be indeterminate. So, that is how these things work. And sometimes if you have, we are talking of cases where the unknowns were more. What happens if you have more equations? If you have more equations, then what will happen, as we will see in the example, either one of them is trivially satisfied, that 0 is equal to 0. You will get something like that, which would mean that even though the system can move along that axis, the forces are acting on it as such that there is no movement, and that is why it is in statics. Otherwise, the system would tend to move along that direction, and the unknown would become the acceleration along that direction, which is not known. So, actually this is all following from dynamics. I have put sigma f is equal to 0 here, actually it is equal to ma, and that also tells you why the forces are being applied if there is a restraint. If there is a restraint, you are preventing the acceleration, and since f is equal to ma, because you are preventing the acceleration, it is providing a force. That is the logic of saying that an unknown support provides a force if it does not allow movement, because f is equal to ma, you are forcing the acceleration to be 0, that is why the force has to be there. So, that was the whole logic. Okay. So, now with this let us take up one example, and then now this is an example from the book. I do not know how much of it is visible, also the units are in FPS units, this is just to illustrate the concept. So, I have taken this, and the reason I copied from the this thing of the book was because the geometry was complex. So, basically here what we have is that at point A there is a pin joint, a 3-dimensional pin joint, on which a board is hanging. This board is hanging there, and it is connected by a cable from point E to point C, and there is a cable from point B to point D, and the coordinate axis, the origin is at point A, the coordinates of point C, point D, point E and point B are given, and the weight of the board is given. Now, the question says determine the tension in each cable and the reaction at A. This is the question. Do you all get the geometry of it? You may have done similar problems in tutorials, or you will do them now. So, we have a board which is hanging, weight is there are 2 cables and a pin support at point A. So, as the solution goes, we will first draw the free body diagram, and then we will apply the equations of equilibrium. Is the problem clear? Let us now look at the solution. So, first we draw the free body diagram. At the point A, there is a pin which is there, that means at A we will get unknown force with some arbitrary direction, which we write it as Axi plus Ayj plus Azk. 3 scalar components. Unknown force with arbitrary direction means in a 3-dimensional case 3 components, and we obviously choose, as you will see in this course, we are following a vector approach, makes life easy. So, we will put everything along x, y and z. So, at A we put Axi plus Ayj plus Azk. Next we have to talk of the tensions which are there. There are 2 strings which are there. So, there is a tension along going from E to C and tension going from B to D. Now, the scalar value is the tension. Do we know the direction of EC and the direction of the tension in BD? We do know because of from the geometry. We know the geometry about EC, the geometry about BD. So, therefore, we can work out the directions of the 2 tensions. That means, I have 2 unknowns, TEC and TBD, or I can call them T1 and T2, it is up to me. Then the other unknown is the force, the weight which is acting at W. So, this is the complete free body diagram, Ax, Ay, Az, T1, T2 and the weight W. Now, of these, when we try to work out how many scalar unknowns do we have, it turns out to be 5. Ax, Ay, Az, T1, T2, these are the 5 unknowns. Now, these directions have been worked out. Do you want me to discuss, or is that okay? Do we all know how to find TBD, the direction unit vector along BD and the unit vector along CE? We have already seen this. So, I am not going to go through this, I will just assume this is just a single scalar along with some unit vector. Okay. Now, the first question which comes to our mind. There are only 5 unknowns, and when I write my equations of equilibrium, I will get 6 equations. So, is this a system which is not in equilibrium, or now when it is a 2D case, we are used to visualizing things. In 3D it is not so, but let us try to look at the x axis. If I look at the x axis, what do you find? All the forces are intersecting the x axis. Is that clear or no? Just see this. The weight is passing through the x axis, the 3 unknowns are passing through the x axis, the 2 tensions are passing through the x axis. That means if I take moments about the x axis of any point, what will I get? 0. So, that means that is one trivial equation which I was talking of, that moments about the x axis of any of these points will always be 0. Okay. So, therefore, that is what is being referred to as that this is a partially constrained system. Actually, the system is free to rotate about the x axis. There is nothing which is preventing in this system rotation about x axis, but in this case, because all these forces pass through, so moments about x axis is equal to 0, but they are acting in such a way that there is no rotation. But if there is, otherwise there could be rotation about x axis, nothing would prevent that. So, that is the, and so now once we know these 5 unknowns, then we can just solve the equations, and we solve the equations. In this case, the best thing would be for you that you just write the vector equations and the scalar components. So, you write sigma fx is equal to 0. So, that you will put ax, you will put the 2 components of tension, their x component, sum of that is equal to 0, sum of y components, sum of z components, and then you have sum of moments about point A. Again, there are 3 unknowns acting at point A, so choose point A as the point about which you take the moments, and you write just the vector equations. And for vector equation, the best thing would be wherever these forces are acting, you call the position vector as r1, r2, r3, f1, f2, f3, and then don't try to physically work out the moment. Just use your maths, r1 cross f1, r2 cross f2, r3 cross f3. So, that is what has been done here. You write sum of all these force moments is equal to 0, automatically the x component will come out to be 0, you will only get j and k components. You have 5 equations, 5 unknowns, you will be able to solve for them. This is how you solve these 3-dimensional systems. Now, sometimes in some problems it may be easier, or life may become easy by that if you take appropriate moments, you may be able to get, for example, in this case, when you take these 2 moments, when you take moments about point A, then these 2 equations give you only the 2 tensions. So, it is not a 5 equation, 5 unknown system in the sense that you have to solve all 5 together. When you solve these 2 equations, you get TBD and TEC. The 2 tensions are solved from here, and then once you know this, you go to each of these equations, there is only one unknown AX, AY and AZ. So, that is how you should solve them. You should not get scared that there are 5 equations, 5 unknowns, what to do. Just look at the system and try to take moments about some clever point or a clever axis, you should be able to get things done. For example, in this case, suppose if this plate was in a horizontal plane and one of these strings was tied, instead of this string was tied at this corner. Then in that case, what you could do is take moments about the x axis is equal to 0. That would have directly given you the tension in this string, because all other forces are passing through the x axis, only weight and this force would not have intersected the x axis. If this was in a horizontal plane, take moments about the x axis, that gives you one tension, and then you can move after that. So, you will have to sort of think a bit before going ahead in these type of problems. So, that sort of completes our discussion on equilibrium. Let us now move to the next topic, which is distributed forces. So far, we have been talking of forces which are acting on a system are acting at discrete points. but actually a force distribution hardly in real life is never discrete. Even when I talk of the finger applying the force on my hand, for practical purposes I say that this is acting at a point, but if I magnify this area where the finger is touching the hand, actually it is not a, it is a finite area, and then I have to look at the force per unit area being applied on small areas on the hand. So therefore, what we have in real life, the forces may not be acting at discrete points, and we have distributed forces, and we could put them in, divide them into three parts. We could call them as line force, or a surface force, or a volume force. A line force, let me say, we will say it's a force which is acting either along a straight or a curved line. It need not be a straight line, but it is acting along a line element. The line element could be straight or curved, and it is continuously acting along the line. It is not acting at one point or 2 points as we have seen in the discrete forces. So here the force which is there, if I represent it as F sub L, this distribution has to be the unit of this has to be Newton per meter, because this is force acting along a line. So if the length, if I go 1 meter along that line, then the force will be FL for that 1 meter length. So it's a distributed force. Similarly, the surface force which we talk of, this would be, I can call it as F sub S. What will be the unit of surface force? Newton per meter square, and the volume force F sub V, the units of this will be newtons per meter cube. So let us start with the linear force, or I shouldn't call it linear, I should say line force. Now of course the most common example is the volume force, which we know, the force of gravity. It is a force which acts per unit volume, okay, and we have to multiply it by mass to get the total weight. So the force which is acting, so in fact that's what we call as the body force, it's force per unit volume. A surface force is a force which acts on an area, and it's specified as force per unit area. Example of this is pressure or stresses which act on surface, which we will see, they are given as surface forces. And a line force is what we say force acting per unit line on per unit length. Now let us look at a line force is a typical force. Suppose I look at a beam, it is there, and on this beam I have a distributed force. W of x is the force W of x is the force per unit length acting on the beam. Now there are two things we would like to find out. One is what is the total effect if I know this function W of x. So x is basically this line. So what is the total, the net resultant or the net force which I get because of W of x? And the second thing which we would like to know is where does it effectively act? Will it act at the center of the beam? Will it act at some other point? So now to find what is the total W of x, what we see is we draw a free body diagram and we look at a section dx. So the total force acting here, this force on this df is equal to force acting due to W of x on a section of length dx at a distance x from origin. So, the total value of d of x will be equal to, sorry, assuming W of x is all in the same direction. So, on this section dx, the force acting is W of x multiplied by dx, and the total force obviously, so therefore, the total force is equal to sum of all df, and this will be equal to integral W of x dx with x going from 0 to L, where L is the length of the beam. Okay, and let us call this as Fr. If Fr acts at a distance x bar from the origin, then what I will have is x bar times Fr must be equal to what? The moment about this, that means it will be equal to integral from 0 to L x times W of x dx. Does everybody see how I got the last equation? The integrand here is the moment about the origin of this section dx. When I add it up, it is equal to taking the integral. So, that is equal to the total moment because of this W of x, and this must be equal to x bar times Fr, if Fr is supposed to act at a distance of x bar. And this you realize, so that means x bar is equal to this, and this is nothing. So, from here what we see is x bar is equal to integral x W of x dx divided by integral W of x dx, and this is nothing but by definition this is the centroid of the loading area. X bar is the centroid, and Fr, this is the area under the integral, by definition is the area under the load diagram, and where it acts is at the centroid. So, therefore, we can get some very simple situations from here. Suppose I have a beam like this, on which I have if I have a uniform load of W newtons per meter acting on a beam, then this will be equal to what? Why is this behaving in a this is equal to WL acting at a distance of L by 2. Is this clear? Because W times L is the area, so that is equal to the force. It acts at the centroid, so WL. Now, if we have a beam like this, and there is a triangular loading. It starts from 0 and becomes W at the end. So, that means the loading here is 0, it becomes W at the end. Now, in this case, once again, if this is L, then firstly this force, the net Fr is equal to W times L by 2, area under this, and it acts at 2L by 3 from O. So, therefore, in this case the net resultant will be okay. We can make in case if we have more complex cases, then we resolve to integration. We will integral Wx dx, suppose if it is a parabolic load, cubic load, something like that, then you just integrate that, and to find where it acts, you will again take the centroid. So, that means you will take integral x times W of x dx divided by the total load, that will give you the distance. Okay. And also sometimes we use a composite formula, which is A1 x1 bar plus A2 x2 bar and so on plus An xn bar is equal to A times x bar, where A is equal to A1 plus A2. You have seen this composite formula for center of mass or composite formula for centroid, that x1 bar is the centroid of A1, x2 bar is the centroid of A2, xn bar is the centroid of An. Then the total centroid of the total area can be given as A times x bar is equal to this. And this goes for even if we have to work out for 2 or 3 components, we can do it along component basis. In this case, of course, all the forces are acting along the same direction. So, there is only one formula for a linear load, but we worked it out like this. Okay. So, now if you have a trapezoidal load, a trapezium type of load, that means you can use this formula. So, example, you find the want to find the equivalent due to this type of a loading. So, one way is of course you work out the equation of the line W of x, you work out the equation and then you integrate this, or what you can do is this is equal to a 10 Newton per meter rectangular load plus a triangular load, and this is equal to 100 newtons plus 50 newtons, this is 20 by 3 and this is 5, and then you use the composite formula to find where it acts. So, a trapezium type of load can be divided like this. Also, if there is a negative sign, then you will subtract things. So, you could have an upward force acting maybe in a reverse triangular way, then you just subtract because of that. So, this formula is a algebraic formula, you can add or subtract if there is a cutout, and this formula actually you must have used to find center of mass in a lot of cases, and in this problems also we will later on talk of center of gravity, and that is where we will use the composite formula again. Now, the other part which I think you would have probably done sometime in your courses, okay, there is one more thing which I could talk of here is, we have done this. If we have pressure, so if you have a surface like this on which pressure on surface. So, we have a surface on which the pressure distribution is given as P. P is the pressure distribution, then the net force due to P will be equal to integral of P times dA, and dA, this is double integral or an what we term as an area integral, and this I can write it as equal to integral P dx dy. That means on the surface I choose, on the surface where the pressure is acting, I choose a small rectangular element whose dimension is dx along x, dy along y. So, that is dx dy actually becomes the area dA multiplied by pressure which is acting at that point, that will give me the total force, and we integrate this will give us the total force. And in this case the effective pressure, so this is what Fr is, and center of pressure is the point where Fr acts, and we have x bar is equal to integral Px dA divided by integral P dA, and y bar is equal to integral y times P dA divided by integral P dA. That means there is a point along this surface the pressure is acting. So, basically pressure is acting perpendicular to the page, and that distribution if that is known. So, P is a function of x and y. Then to find the effective point where the single force acts, you will put x bar is equal to integral P x dA divided by the total force, that will give you the x component of the point, and the y component you do the same thing, y P dA divided by integral P dA. Now, in the next class I will take the concept of body force and the center of gravity, take a couple of examples of finding centroids for gravity, maybe some of this will be done in your tutorials, and then we will move ahead from there and move to the next topic. So, we have almost completed chapter 5 now. Okay. Yes. Yeah, you have not done this?